So maybe we can continue to the last talk before the dinner tonight with Ian Melbourne, currently visiting for some longer period São Paulo, talking about non-standard functional central limit theorems.
Now? Does it make a difference? Yeah, okay. Anyway, thanks very much to the organisers for the invitation. It's always great to be in Rio de Janeiro. I'm going to talk about some non-standard functional central limit theorems that come up in certain dynamical systems. My collaborators are the famous Portuguese author Yuri Lima and Carlos Mateus. So I'll start off with some examples. And the first example is from dispersing billiards. It's called the Bunimovic Stadium. So you have a rectangle of size L and 1, and you have two hemispheres. So we glue them together to form the shape like this. So that's the stadium, and that's I'll denote that by omega. And the phase space is the boundary. So the phase space is x is equal to, you have a point in omega, in boundary of omega, and you have a direction. So it's cross. So it's a two-dimensional phase space, the boundary of the stadium, and angles between plus and minus pi over 2. And I'll call these r and theta. So r is the arc length along the boundary of the stadium, and theta is the angle to the perpendicular. And then what you do is you imagine this particle just moving in a straight line until it reaches there, and then it just bounces with the same angle that it left with. So you start off with a point and an angle, and it maps to a point and an angle when it hits the next when it makes a collision. And so we have a dynamical system F that goes from x to itself. And then we have a measure. So we have the Liouville measure, which is the mu is cosine theta dr d theta, and that's an ergodic invariant mixing measure. So it's ergodic. It's F invariant. Oh, and normalized to make it a probability measure. Normalized to make it a probability measure, and then it's F invariant, it's ergodic, mixing, and so on. So that's the dynamical system, and then we have an observable, V, which goes from x to r, and I'll assume that V is Holder, and that the integral V d mu is 0, centered. And then define the Birkhoff sum, V sub n, to be the sum j equals 0 to n minus 1, V composed with f to the j. And then the Ergodic theorem says, of course, that V sub n divided by n will converge to 0 almost everywhere. And so, like in Pablo Carrasco's talk yesterday, we might look for a central limit theorem. But this system is it's certainly not uniformly hyperbolic. It's not partially hyperbolic or anything like that. There's going to be lots of periodic orbits that just run backwards and forwards, bouncing between the two parallel sides. And if you come in at some angle, you're just going to go like this for a very long time. So the dynamics is going to be very rigid, and that leads to anomalous behavior. So what we do is we define I sub v to be the integral over S of V of R0 dr, where S is just the union of the horizontal parallel sides. So what we're doing is we're basically averaging over all the values of the velocity field in these vertical directions, of the observable in these vertical directions. And that kind of measures how the hyperbolicity is breaking down in the most important way. And then there's a theorem due to Peter Balint and Sebastian Guzel in 2006, which says that if IV equals 0, then you get the standard central limit theorem. So 1 over square root of n, v sub n, converges in distribution to some normal distribution with mean 0 and variance sigma squared, where the variance might be 0, but that's extremely rare. So sigma squared greater than 0 typically. And this means it's actually the same as Pablo Carrasco described yesterday. It means you're taking the measure of all the points r theta in the phase space such that 1 over square root of n v sub n of r theta is less than or equal to constant. And this is the kind of distribution function of the left-hand side, and you're asking that converges to the corresponding things on the right-hand side, the probability that the Gaussian lies in the interval minus infinity to c. So you just have to look up the density for the Gaussian, and it's something like this. Okay, so that's what the convergence distribution means here. So that's the standard CLT. But if IV is not equal to 0, I mean, what the vanishing of IV means is that somehow the observable is not seeing what happens in this kind of region where you're just bouncing backwards and forwards. If IV is not 0, then you do see it, and then this implies that you get a non-standard CLT, and you have to normalize by something a bit bigger. Now, unfortunately, I can't do Balash's log symbol. I think you need a bit of practice, but I'll just write it as log. 1 over square root of n log n, and this converges in distribution to n0 sigma squared, where sigma squared is just some constant that depends on L times IV squared, and C of L is positive. So in this case, there's actually no chance that you get a degenerate central limit theorem. It's always non-degenerate. The variance is always basically just a constant that just depends on the stadium times this quantity IV squared. So the thing is, you get this anomalous behavior where things grow super diffusively. They go faster than square root of n, then you have to normalize by an extra square root of log n. So this was the example of Balint and Guzel in 2006, and there have been various examples that have come up since then. And so the next example I wanted to mention was billiards with cusps. Are there any questions before I move on to the second example? Yeah? The motivation is this, well, mainly it's a nice example, that certainly Sinai in the 1970s introduced dispersing billiards, and there's lots of papers on dispersing billiards where you could really see that there's going to be a lot of stretching and lots of contraction and expansion. But in this example, there's actually no obvious mechanism for expansion and contraction. So it's supposed to be quite surprising that this example actually produced any kind of hyperbolic dynamics at all. And it becomes from this focusing mechanism where this semicircle kind of focuses things to the center, which makes things get closer, but then they go through and then they get separate. And so there is a separating mechanism of trajectories by going through this origin of the semicircle. But nevertheless, you have to prove quite a lot to show that this has nice properties. Anyway, it's become a classical example in dynamical systems.
The constant Cn when L goes to 0, because when L goes to 0, you're approaching the disk.
Yeah, so we definitely don't want to take the limit as L goes to 0. We fix an L positive, and all the statements I made are just for that. And certainly it's going to get messed up because then you're in an elliptic case. Yeah. Right. Any other questions? Okay, so the second example I want to talk about is billiards with cusps. So here what we have is we have kind of strictly convex things, scatterers, but they kind of touch each other. And maybe there's one cusp or several cusps, maybe some of the corners are a bit more finite. I don't want that to be a straight line, but you could. So I've drawn a table here with 4 corners, but 2 of them are cusps and 2 of them have got positive angle. But that's not important. It doesn't matter how many cusps and how many corners there are. And you do the same thing. You do exactly the same thing as here. You play the billiard game where you have r's and theta's around the outside. So I don't need to write anything out. It's exactly the same kind of dynamics as before. Here, but this time the anomalous stuff stems from the fact that you get stuck in the cusps, and you go into the cusp and you take a long time to go out. There's not a lot of mixing going on while you're in the cusp, but then once you're out of the cusp, then you start bouncing on these convex or concave boundaries, and that produces dispersion. And you get ergodicity and mixing and everything. And you do the same things before. You define the Liouville measure just as before. You consider Holder observables. We define this. We'll have a more complicated formula for I sub v. So I won't write down what I sub v is, but there's a formula for I sub v depending on each of the cusps. And then you have some similar theorems. So this time it's due to Balint, Chernov, and Doga-Piat in 2011. And they again got that that the corresponding version of IV equals 0 implies the standard central limit theorem, i.e. that with the usual normalization, the Birkhoff sums converge to the Brownian, to a normal distribution with a variance that's typically positive. So whenever I say standard CLT, it means all of this. V sub n defined in the appropriate way, and some positive variance, at least typically. And then, if IV is not equal to 0, they got the standard, non-standard CLT. So they got the extra logarithm on the denominator, and again converging to a normal distribution where it depends on some constant that's just, this constant just depends on the table, on the table that we're doing the billiards in, multiplied by IV squared. But they also proved a bit more. They proved the non-standard functional central limit theorem. So, to explain what that is, so what you do here is you define a process or sequence of processes, Wn, going from C01 into, just in C01. So maybe I just write it as going from 01 to R continuous, where I define W sub n of t to be 1 over square root of, that talk didn't do very well, 1 over n log n, v nt if t is equal to 0, 1 over n, 2 over n, up to 1. So you look at all the integer multiples of n, of 1 over n, and each time t increases by 1 over n, you put an extra term in the Birkhoff sum. And then you normalize by 1 over square root of n log n, and you view this as a function of time. So this gives you a load of dots, and then you linearly interpolate. So you join the dots to form a continuous function, and that's the thing w sub n. So we end up with a thing, wn, which lies in C01. But of course it's random again, in the same way that we had randomness in v sub n. V sub n just depended on the initial condition, and this w sub n is now a continuous function that depends on the initial condition. And then the functional central limit theorem, Nonstandard functional central limit theorem, is that Wn converges weakly to W in the space of continuous functions. So you view it as a random object in this more complicated space, and here this was saying that the measure of this thing lying in the interval minus infinity c converged to the probability that the normal distribution lied in the interval minus infinity c. And here we're saying that there's some object, which is the Brownian, called actually a Brownian motion, such that the measure of initial conditions, such that w sub n lies in a nice subset of the space of continuous functions, converges to the probability that w lies in that nice subset of continuous functions. So that's a very rough description. Yes? The w is it doesn't really, W is a Brownian motion. Yeah, so with a variance sigma squared. So it doesn't really matter for this talk, but the point is that there's some limiting object, which is what's called a Brownian motion. You can view this as being a definition of Brownian motion, if you like. And this sequence of random objects in this more complicated space converges in distribution to this limit. So it's called the functional central limit theorem. The functional central limit theorem implies the central limit theorem. And the reason it's called the functional central limit theorem is because you could take a continuous real-valued function on the space of continuous functions and apply it to this side, and it converges to the continuous function applied to that side. So for example, if I took the function that evaluates at time 1, w sub n, if I evaluate at time 1, is 1 over square root of log n v sub n, which is precisely what I have over here. Brownian motion evaluated at time 1 turns out to be this object. So the functional central limit theorem implies the central limit theorem, but it's much, much stronger because there's lots of other continuous functions that you could consider. So are there any other questions about that? So, okay, good. So that's what they proved. So that's example 2. And example 3 is the example with Yuri, Carlos, Mateus, and myself. We haven't completely finished writing it down yet, but I'm absolutely confident it will be finished this month, so certainly by the end of this year. And it's a geodesic flow on a surface with mainly negative curvature, but a bit of flat bit as well. So it's something that looks a bit like this. So there's some kind of flat region, and so this is like a cylinder. Well, it is a cylinder, and that's flat. And then we put some slightly bigger cylinders here, bigger circles here, thicken it out in a nice, reasonably smooth way, and then glue on some hyperbolic surfaces at the end. So I made this genus 2, but it could have any number of holes. It doesn't really matter what this looks like, provided it's hyperbolic. So you have negative curvature everywhere except on the cylinder. So I can be a bit more precise. I need to be a bit more precise. So what we do is we have a profile, psi, that goes from minus L minus A, L plus A into R. And it looks like psi of S is equal to 1 if S is between plus and minus L. And it looks like 1 plus S minus L to the R if L is less than or equal to S is less than or equal to L plus A. So I'll tidy that up a bit. That should be over here. So this profile looks like that. And then we take this profile and rotate it to form the surface of revolution. So that's going to give this. And then we just glue on these regions at the end. So that's the example. This gives you a two-dimensional surface, S. We have some, I should call it X for consistency, I guess, is the is going to be the unit tangent bundle over S, and then you form the geodesic flow. On this three-dimensional manifold. And I'm going to assume for technical reasons that this R is greater or equal to 5. And then we do the usual thing. Okay, we have the mu is just going to be the volume measure. And that's going to be a nice ergodic invariant probability measure, mixing, etc., Bernoulli, whatever. And we have V goes from X to our holder, integral of V d mu is equal to 0. I should give the geodesic flow a name. Let me just call it F sub t. And then if I instead of doing Birkhoff sums, because it's continuous time, I do a Birkhoff integral. I define V sub t to be the integral from 0 to t of V composed with F sub s ds. And then I might normalize by square root of t or square root of t log t, depending on what theorem I want to prove. But then we define I sub v to be the integral from minus L to L of, and I'm not going to try to define things precisely, but hopefully you'll get the idea of what this notation means. I don't want theta, I want the 0. Yeah, I do want theta, sorry. And V, missed out the V's. Okay, what else have I written down here? Well, S is my coordinates along the cylinder, in the same coordinate as up there. Theta is the angle of revolution around the cylinder. The bad geodesics are the ones that either wrap round like this, going in a counterclockwise direction around the cylinder, or the ones going the other direction. There's two families of geodesics that lie completely inside the flat region, and those are the things we're integrating around over here. So we're integrating around all the cylinders at every point along the axis of the cylinder. We have a periodic solution that goes round it one way and round it the other way, and we just sum up over those. And that's going to be our I sub v. And then the theorem is that is that if IV is equal to 0, then we get the standard CRT, and if IV is not 0, then this implies the non-standard CRT and also the functional CRT, the stronger result. So that's our theorem. Any questions about that? Okay, well, there's one bit that was missing, right? Because, yeah.
You get a functional CRT if EV is 0.
We're not claiming that, and I think there's good reasons to believe the answer is no. Because but I'll explain why later. I'll answer that question. But that's one thing that's missing. In all the standard cases, I'm only claiming the CRT. But in the non-standard cases, I'm claiming that you actually get the functional central limit theorem in the non-standard case. But that was only stated for the geodesic flow, example 3, and example 2, the billiards with cusps. For the Bento stadium, the theorem by Bento Gonçalves only claimed the non-standard central limit theorem, not the non-standard functional central limit theorem. But that turns out to be a corollary of our method. So, So a corollary of the method, and this is actually in our paper that was already written last year, is that for in example 1, the Bento stadium, if that quantity IV was not 0, that implies the functional central limit theorem. So in 2006, Bento Gonçalves got the central limit theorem in this situation, but we're claiming that actually 20 years later that you get the functional central limit theorem. And part of the reason we get this is because we had a lot of trouble with reading the old papers, and so we tried to come up with something that worked with doing as little work as possible. And it turns out that once you only need as little work as possible, you find out that Bento Gonçalves actually did all the work that was required to prove this. So we were able to read it off from what they'd done and from our method of doing things. So that's the examples. So I'd like to at least try to explain part of the strategy for how we approach this problem. I'm sorry, I didn't hear.
In the first case, what happens if you observe all this anomaly?
In the case where IV is equal to 0, where you get the standard CLT, it might be a boundary, co-boundary, then you get variance 0, but that's extremely unlikely. The question was over there, right? So, yeah, so it's one of these situations where there's infinitely many obstructions. To be a co-boundary in the cases where in this case, this kind of situation, to be a co-boundary, you'd have to lie in a subspace of the Holder functions of infinite codimension. Right, good. So now I've lost the basic. Right. So I'm going to try to explain parts of the strategy, and to start with, I'm going to think about a much simpler example. So this is example 4, which is a one-dimensional map. It's a so-called intermittent map, which was introduced. The idea of intermittent maps was introduced by Pomeau and Menville in 1980, and this is a typical example which was studied by Liverani, Sassou, and Vaienti in 1999. And the idea is that there's a neutral fixed point at 0, and everywhere else it's uniformly expanding. So a formula would be, so x is equal to 0, 1. F of x is equal to x 1 plus 2 to the gamma x to the gamma if x is less than 1, and 2x minus 1 if x is less than a half, x is bigger than a half, and gamma is a parameter that's greater or equal to 0. So if gamma is equal to 0, this is just a doubling map, which certainly is very well known to have the central limit theorem and lots of good statistical properties. And the idea is as gamma gets bigger and bigger, this becomes a neutral fixed point, and it becomes stickier and stickier. And it's kind of well known that if gamma is less than 1, then there exists a unique, absolutely continuous invariant probability measure, mu. And if gamma, now I'm going to let V, so that's going to be my ergodic measure. As usual, I'll let V go from x to r be Holder. Integral of V d mu is 0. And then if gamma is between 0 and a half, strictly less than a half, then there's no anomalous behavior. So you get the standard CLT, functional CLT, and lots of other things as well. So things only go wrong. The mixing properties get slower and slower, but you still have the standard central limit theorem for the whole region from gamma from 0 up to but not including a half. And then half is a threshold. So gamma equals a half, then it turns out that's the situation where things become sticky enough to produce anomalous behavior. And the observable sees it if V is non-zero, if V is non-zero at the origin. So an analog of IV is just going to be the value of V at 0. If IV is equal to 0, that means that V vanishes at the origin. You're not seeing the sticky behavior, and you just get the standard CLT. In this case, you actually do get the functional central limit theorem, but I don't want to, that kind of ruins the story for everything else. So let's just keep it the same, standard CLT. And if IV is non-zero, then you get the non-standard CLT. So these were proved by Grisel in 2004. And you also get the non-standard functional central limit theorem, and that was proved by Dedeker and Merlivade. In 2009. But their technique, Dedeker and Merlivade are probabilists, and their techniques were very probabilistic. And what I want to do is show an argument which is different from what they did, which is kind of how we approach all the other problems. So our method for proving this is to, first of all, there's a standard technique called inducing. So we let Y be the set a half 1, and we let tau go from Y to Z plus to be the first return time. So it's the tau of Y is the infimum of n greater than or equal to 1, such that f to the n of Y is contained in capital Y. So as I said, the thing is, we've got an invariant measure, so by Poincare recurrence, this thing is going to be finite almost everywhere. So you have this well-defined first return time, and then you define the first return map. F goes from Y to Y, and this is going to be defined to be f to the tau. So f of Y is just you take f to the correct number of iterates applied to y. Okay, so it's like a Poincare map, but in discrete time. And this map, capital F, is a nice map. It goes, there's a half, 1, 1. From 3/4 to 1, it's just going to map the interval 3/4 to 1 onto the interval half to 1. But then you're going to get a load of other branches. So there's actually going to be infinitely many branches, but they're very well controlled. The slope is greater than equal to 2, because you always pick up a derivative 2 over here, and then you can't decrease the derivatives because these are all bigger than 1. So it's nice and uniformly expanding with good bounded distortion properties. So the log of the Jacobian is the holder, the log of the Jacobian is holder, so you have very good hyperbolicity properties. So the map F is very good, so you could hope to prove things for the map F. It's what is often nowadays called a Gibbs-Markov map. It's basically full branch, possibly infinitely many branches, but with nice uniform expansion and good bounded distortion properties. So that's a nice map F for proving things on. The map tau, it turns out you can figure out the distribution function of tau, how big tau is likely to be, turns out to be asymptotically a constant divided by n squared, where the constant is greater than 0. So this asymptotic means that if I take this side and divide it by that side, it converges to 1. And so one thing you can notice is that because of the 1 over n squared, that kind of implies that tau is in LP if and only if p is less than 2. So in particular, it's not in L2, which is why you might expect the central limit theorem to fail for this map. And so there's a theorem of Arrington and Denker, (2001), which says that tau satisfies the non-standard CLT. So this is now tau viewed as an observable on the induced map. We started off with a map little f going from x to x. We replaced it by an induced map, big F, going from y to y. And we're saying that if we now view this tau as an observable on y, then it satisfies the non-standard CLT. And basically the requirements from Arrington and Denker is that your dynamical system is Gibbs-Markov, that you understand what the tails of tau look like, and that tau is constant on the partition elements for the branches of the Gibbs-Markov map. So all of these conditions are clearly satisfied. And it's a relatively easy exercise that we did, because we couldn't find it in the literature, is that you have enough structure here that tau satisfies the non-standard functional central limit theorem. So somehow there's a claim that this is a situation where such theorems are easy to come by. If you've got this nice uniformly expanding structure, and you've got a nice piecewise constant function with respect to the partition with the correct tails, then it's not so hard to show that tau satisfies these non-standard limit laws. And then, if you've got your original v going from x to r holder with mean 0, then you induce the observable. You define v hat goes from y to r just by defining v hat of y is the sum 0 to tau of y minus 1, v composed with fj. So you just you just track what happens as you do enough iterates to bring you from y back to itself. So if you think of the Birkhoff sums of V, then V hat is just a chunk of the Birkhoff sum. But you can now, if you look at now, you can do a calculation, and I'll just write down the answer. V hat of y is V of 0 times tau of y. Okay, well, actually, I'll write it down. Sum 0 tau of y minus 1, V composed at f to the j of y minus V of 0. So just add V of 0 and subtract V of 0. One term just gives you a constant times the number of iterates, so tau of y, and the other one gives you something like this. But because this is Holder, you can just boil it down to the sum of the iterates of the sizes of f to the jy, and if you understand that well enough, then what you can hope, and what turns out to be easy to prove in this situation, is this lies in L2. And this thing, of course, V of 0, is what I called I sub V. So you see that what happens is that the induced observable just looks like the first return time plus something that ought to be negligible because it lies in a higher LP space. And then this readily gives you the CLT, FCLT, etc. for capital V hat, because the dominant term is the one over here. You just get it with a different variance that depends on the value of I sub V. And then there's well-known techniques that show that once you've got a central limit theorem or a functional central limit theorem for the induced observable V hat, it's straightforward to reduce it back to the original observable V. So this gives you the same for V. So this is part of the strategy. And the point of the strategy so far is that you don't have to work with general observables V. You just have to understand what happens to tau, what the first return time does. And that first return time turns out to be the important part of the whole calculation. And that has advantages that tau is defined on a Gibbs-Markov map and that it's piecewise constant, which makes things a lot easier. So to summarize, you have that you have an f equals f to the tau goes from y to y, and that should be Gibbs-Markov. And measure of tau greater than is like some constant over n squared, where the constant is non-zero, and that the induced observable looks like I sub v times tau plus negligible. These were the ingredients that we used for proving the result, and it turns out that in all the examples I mentioned, all of this structure holds. But there's a slight complication, which is that tau need not be the first return time. In the examples 1, 2, and 3, the billiard examples and the non-geodesic flow example, this is not the first return time, it's just some good return time. And that good return time is given completely non-explicitly. And because it's non-explicit, computing mu of tau greater than n is hard. Or you can't do it directly. Whereas you could do it directly in this case because tau was somehow given geometrically. In these examples, it's not. And so, there's an extra part, which is strategy part 2, which I'm not quite sure if I've got really enough time to do it, but I'm going to start and see how far I get. And it's based on an idea of Markarian from 2004 when he was trying to understand, I guess, the Bunyamovic stadium. But let's look at billiards with cusps, because that's easier to draw the picture. I don't know if that looks legible at all, but this is supposed to be my original billiard with cusp space, but what I've done is I've drawn a neighbourhood of all the cusps, and I define x tilde to equal x minus neighbourhood of the cusps. And then what you do is you let f tilde go from x tilde to x tilde be the first return time. So you introduce an intermediate first return time. That should be f to the tau tilde. So I introduce a tau tilde, which is the first return time to this x tilde, and that gives me a first return map f tilde. So this is a first return map with tau tilde being a first return time. And the idea is that because this tau tilde is given geometrically, you can actually compute how long it takes to make the return. You can compute that mu of tau tilde greater than n is some c tilde over n squared, where c tilde is positive. So in all the examples, there's a nice first return time which is geometric, and you can actually figure out the tails of tau tilde. But you're not finished, because x tilde is still not a Gibbs-Markov map. So then you write x tilde as y to the a new time phi. So x tilde, sorry, I didn't mean to write that. I meant I get a y contained in x tilde, which was contained in x, and you get f tilde equals capital F to the phi, where capital F going from y to y is basically Gibbs-Markov. It's not quite Gibbs-Markov because there's contracting directions as well as expanding directions, but let's just ignore that. So you have this Gibbs-Markov map. So you take a first return time and then you reinduce it to get a Gibbs-Markov map. This phi is a good return time, not a first return time. But it has exponential tails. Measure of phi bigger than n is e to the minus an, where a is positive. So this is basically the idea of Young, Lysan Young in 98. You try to model it by what's called a Young tower with exponential tails. That's basically something that's got a Gibbs-Markov base and a return time that's exponentially good. And now you write f, well you write the divisional f, which was f tilde to the, no, you write, getting my variables, I got these the wrong way around, that's f and that's f tilde. Okay, so I induced f tilde to get f, I induced f to get f tilde, and now I induce f tilde to get capital F. If I do it all in one go, I have f equals f tilde to the phi, but f tilde was f to the tau tilde to the phi. And so combine the inducing times to get your f to the tau. So you get some tau, which is somehow some combination of tau tilde that we understand completely and phi that ought to be negligible. But usually this isn't enough to give you the good tails for tau. But there's a trick. So, and that's where I'll stop. I'll say that I claim that the measure of tau greater than n is asymptotic to c over n squared, and the proof is basically that, and I have to assume something, suppose that tau tilde satisfies the non-standard CLT. Okay, so this is the big assumption that I have to make in the end. I don't care about functional central limit theorems. I don't care about Holder observables. I don't care about the tau. I just care about this tau tilde that we started with over here. If you, by hook and by crook, can prove that this tau tilde satisfies the non-standard central limit theorem, then the claim is that everything falls into place. That actually this tau, which was not defined in any nice way, must have the right tails. And the proof is that because tau tilde satisfies the non-standard limit theorem, by inducing in the reverse direction, you get that tau must satisfy a non-standard central limit theorem. But tau is a locally constant function defined on a Gibbs-Markov map, and it turns out that on the Gibbs-Markov map, satisfying a non-standard central limit theorem is equivalent to having the right tails. So it's kind of done in some very roundabout way. You prove this, which certainly Ballantyne, Grisel, and everybody else managed to do. You deduce that because this satisfies a non-standard central limit theorem, therefore tau must on the space Y by this inducing idea. But because tau is defined on such a nice dynamical system, you can prove an if and only if result. That's due to Grisel in 2010, that because tau satisfies a non-standard central limit theorem, it must have the right tails. And that was the missing ingredient, and that's why everything works. And that's why we get the non-standard functional central limit theorem for the Bunyamovic stadium as an immediate corollary of this method. So I'll stop there, so thanks.